So let's write it here. Combination of springs. Now we have basically two systems. First system we call that series, and the other one is parallel, like that. Series means that you have two or more springs, one after another. Like you have a spring like this, and then you have a spring like this. And there is a load that is attached to you. So that applies some force. Alright, like that. Parallel would mean that you have springs that side by side taking up the load at the same time. So you have one spring like this, and you have another spring like that. And for this one, we are going to pull them together with the force F like that. Is it clear, everyone?
Yes.
Okay. That's good. Now, so in series, I'd like to tell you that whatever force you see F is the same everywhere. So we're going to say force F in each spring will be same, like that. Which means that if this is like spring K1, this is spring K2, different stiffnesses doesn't matter. So what's different is that each spring will show a different extension. So this will have extension S1, this will have X2. So we can say the total extension of a spring system in series would be X equals to X1 plus X2 and so on. Get it? You guys?
Yes.
Now this derivation that I'm going to do is required by the examiner, so you guys need to remember this. F is equal to kx, so x will be equal to f upon x. So here we can substitute f over k equals to f over k1 plus f over k2. Now each spring basically takes up the same force, that's why we're writing f. And when you cancel out f's together because you can take common, so it's gonna leave us with, let's cancel them out. It's gonna leave us with 1 upon k equals to 1 upon k1 plus 1 upon k2 and so on. So this is how you can find the total spring constant. Right. Then next, when you have parallel system, in parallel system, you guys need to remember that force is divided between two springs, and it is not necessary that force is divided equally. It could be different, but extension is same if pulled together. Obviously, if you want to pull them together, this is K1, this is K2. So they're gonna show you the same extension like this. All right. So what happens is that when you write the total force, so the force Kf will be divided such that the first spring will get F1, the second spring will get F2. And if there were more, they would get more, right? Then, because F is equal to Kx, so I can write here Kx, I can write here K1x, I can write K2x here, like that. Furkan, why are you always late in the class? Interesting. Now, because x is the same quantity, because the extension in each string was the same, so you cancel out x. This will basically give you k equals to k1 plus k2 plus, depends on how many springs are there. So these are the derivations that are required by the examiner. Is it clear, everyone? Please let me know if you have a question here.
Yes.
So if we have the total force, then how do we find the force divided among the two springs?
Just like this, you're gonna find the total. You're gonna have total extension, right? So extension will be same. If you know the spring constant, you can use F equals to kx. Then you get it.
Okay.
Yeah. So one of those two, three things, those two things will be given, right? Out of those three. Now let's do a question on this, and then we're gonna move on. So it says a number, a number of identical springs are given. Find extension in terms of k in each system. Alright, so this would be the question. So you have for the first one given like this, and mind it, they're all the same type of springs. If they've said they're the same type of spring, which means that they will have the same K. The next one is like this. They're taking up the same load as well. Just make it a bit smaller. Okay. Move it a bit here. Now three. And four. So I'm gonna basically do uh, one and four. You guys will do two and three actually, just to see what we're doing. Okay. So let me try the first one. So obviously they all have the same force, which is L. They have the same K because they're made of the same spring. By the way, same material, same type of spring. So we can say, because in series, I know that 1 upon k total is equal to 1 upon k plus 1 upon k. It's k1 and plus k2, right? So 1 upon k total then will be 2 over k. So the total spring of the whole system, spring constant will be 2 by, k by 2. My bad. Just like that. Then I'm going to use f equals to kx. This is L, this is k by 2, and x is what we need to find, right? So x will be equal to 2L over k. Do you guys get it?
Yes.
Good. Now I'm going to do the last one, and then the rest two you will tell me the answer though. So the last one, because this section is basically parallel. So in parallel, the springs in parallel will be k plus k. So it's 2k. And then when I've solved this section, I'm going to solve this whole thing in second part. So the 1 upon k total, because it's in series, 1 upon 2k plus 1 upon k, like that. So this LCM will be 2k, this will be 1, this will be 2, 1 upon k total. So the k total in this one will be 2k over 3. Now I will use f equals to kx. This is L, this is 2k over 3. I want to find this extension. So this will be 3L over 2k, like that. You guys get it?
Yes.
Okay. Alright, now I want you guys to do 2 and 3. Give me the answer, please.
So I got an answer.
Okay. Yes, go ahead.
2 is L over 2k,
That is correct. And
and 3 is L over k.
L over k. That is correct. Very good. Anyone else who could do this and who's stuck? Please let me know. Okay. So it's pretty easy. The second one is because it's just parallel one. So the total k in this will should be k plus k, because in parallel you just add them directly. And then you just need to use f upon kx. This will be L. This will be 2k times x. So x will be L over 2k, like that. For the next one, it is basically these are in parallel, and this is also in parallel. And then what I'm going to do is I'm going to add them together as series in the third step. So first one, for the first step, the parallel k's are 2k. For the second step, the parallel k's are 2k. Now k total for the third step is 1 upon k total over 1 upon 2k plus 1 upon 2k, like that. You take LCM as 2k, this will be 1 plus 1, and then take reciprocal. So you're going to end up with 2k over 2, which is just k. So now you can do f upon kx. This is L, this is K, this is X. So X will be L over K. Any questions, anyone? Please let me know.
No.
Very nice, very nice. All right. Okay then. So then we are gonna move towards the next. You guys can copy this, and then let's see. Okay. All right. So the next thing we're gonna do. You guys have copied this. Should I go forward now, please?
Yes.
Okay. So we got basically elastic limit. So elastic limit is a point beyond which the material does not return to its original shape. We can say that after this it is permanently deformed, and it basically permanent deformation has another word. It's called plastic deformation. Now it will just change its shape forever. Is it clear, everyone?
Yes.
Generally speaking of this, when you have the graph that we studied before, suppose this is extension.
So this is specific to spring, right?
No, every material.
Okay.
This is force. So if you keep on pulling something for like quite high load, at one point we've studied it starts to turn. So the first point that stops following Hooke's law is limit of proportionality. You guys know that already. And just after this, you have elastic limit. So limit of proportionality and elastic limit are different things. Just after limit of proportionality, we get elastic limit. Is it clear, everyone?
Yes.
Farina, you also understand Shazib, Furqan, Zilwa.
Yes.
Furqan, are you there? Shazib and Abdullah. Hmm.
Yes.
Okay, good. Oh my god. Wait a second. While you write this, charger on. Interesting. Okay. Done, you people?
Yes.
Okay. Now let's go forward. So when you see elastic limit, we can then basically find the energy from this. The name of the energy that we have here, it is called elastic potential energy. But I just want to tell you that elastic potential energy has another name, which is strain energy as well. So basically, it's the same thing. Okay. Now, Shazib, are you there? Shazib, why can't I hear you? Okay, good. Now, so let's have a look. So let's suppose if I draw a graph of force and extension, force in newtons, extension x in meters. So you'd see that basically the graph is gonna go like this, and then it starts to curve like that. All right, that we have studied before as well. So the point where limit of elastic limit comes, that's E. Just underneath it, this section of the graph is called the strain energy. Is it clear, everyone?
Yes.
So is that limit of proportionality or elastic limit?
Elastic limit. Limit proportionality just comes before that. It's here. You get it?
Okay.
Elastic limit is just here. And the rest of it, if they ask you what exactly is the whole thing, so the area under the full graph gives you work done, or you could say total work done. All right. Just remember that area under the triangle section, right, is strain energy. Because this energy basically is something that can cause the object to come back to its original shape. So this is something we need to remember. So we're gonna basically see that this energy will be equal to half times, this is some force obviously, it will have some extension. So half times force times extension. You guys get it?
Yes.
So the area under the full graph, is it the energy needed to like deform the spring?
No, this energy is also deforming the string. You get it? It's also deforming the string. But the point is that if it stays within this limit of elastic limit, it is going to come back to its original shape. Beyond that, it won't come back to its original shape, right? So beyond that, your work done is going to cause some changes in the structure of that material. So it will start to change shape permanently. Do you get it?
Yes, so the within the triangle it will not be deformed, right?
Yes. For example, let me tell you how materials work, right? So you have an idea what you're asking me now. I understand why you want me to answer that. You see, if you stretch a material, so suppose originally a material looked like this. Okay. Let's talk about these part. So when it goes stretching, basically the material would still be in on its own shape like that, right, Himal? Just that the average spacing has increased, you see,
Yes.
compared to this one. But when it goes into this region, which is when it becomes plastic, not the basically plastic material, plastic means permanently deformed. So it means some layers are gonna get slipped like that. Do you understand?
Yes.
So when they slip, now they will permanently change shape because they cannot come back to its original shape. Understood?
Yes.
So it's sort of a change like that. Now this formula is used, but not as often as the other ones. Furkan, can you hear me now?
Yes.
So if you basically put f equals to kx into this, replace f. So you get another formula which is widely used in exams, which is half times, instead of f, I'm going to write kx times x. So the energy will be half times kx squared. So these two formulas are very important. Uh, the second one is mostly used, but the first one is also sometimes used. There's an energy formulas. You can write that down, please. Okay. All right. Now the questions which are gonna haunt you most of the time. I just want to tell you that you guys have written it. Should I go forward now?
Yes.
So in a lot of questions, they're gonna ask you about change in strain energy. Change in strain energy. Now, usually there are two ways that people basically often adapt to. So there has to be a correct way and there is a wrong way. I don't want you to follow the wrong way. So the correct way of doing this is that the change in energy must be taken like this. So you have to subtract energy 2 minus energy 1. So when you write the formula, it would give you half kx1 square minus half kx, sorry, 2 square minus kx1 square. Right. So I'm just talking about sort of question where they will ask you to find change, like they have given you force and extension graph, and then they've shown a line. They have shown you two different sections, x1 and x2, and they want you to find the area and the graph of change here. Do you guys get it?
Yes.
So when you do that, you'd see that if you take half and k common, so you're gonna get x2 square minus x1 square. So this is basically a mathematical function that represents a square minus b square. You guys get it?
Yes.
But what most of the people do, that they find the change here, so that they write, let me write it with a different color. So they tend to write delta x equals to x2 minus x1, and then they think that the change in energy will be half times k delta x square, right? So when they write the formula, it becomes half k x2 minus x1 whole square. Now, if you notice, both formulas are completely different because this formula basically represents a mathematical function of this, which is completely different function. It will give you a wrong answer there. Is it clear, everyone?
Yes.
So do not do the first one. Whenever you're finding change in energy, you got to find change in energy, not the change in extension. Okay, write it down, please.
So what if they have given us the force and not the spring constants?
Then it is easy. You can find that. You can find energy by one force and then the other one, and then subtract them. It's okay. But if they really want to test you, which they will test you through this one. Get it?
Yes, sir.
Okay, write this down, please. All right. Abdullah, you okay with everything? And Fatima, what about you? Asma, everything is clear? That's good. That's good. All right. Now I'm gonna go to the question. So this is a very famous question. So this will clear a lot of confusion in your mind as well. So let's do this example. So basically, so they say there is a trolley which is right now at equilibrium, and it is in equilibrium such that there are two springs. Let me change the color for the springs for better understanding. They are currently, extended already. Like that. The mass of this trolley is 850 gram, like that. Okay. So they're saying when the trolley is in equilibrium, so look, each spring is extended by 4.5 centimeter. So it's already extended with this in equilibrium. Each spring has a spring constant of 16 newtons per centimeter. They've also given that. Now they say the next point, the trolley is moved a distance of 1.5 centimeter along the direction of the springs, like that. This causes extension of one spring to increase and other to decrease. Is it clear, everyone? Then they say the trolley is released and reaches its highest speed. Calculate that speed. Now this question is pretty confusing, but it's all right. Let's understand that by a couple of things. What they're basically saying is that if the trolley was moved, let's assume the trolley was moved this direction, doesn't really matter where it moves. Initially, you guys need to remember that if this is the trolley right here, initially the extension in both the springs is 4.5 centimeter. This is the extension, not the length, by the way. 4.5 centimeter. Both springs have the same extension. If you move the trolley to either side, and now you basically cause it to move by 1.5 centimeter. So if you're moving it here, the extension in this will decrease. So the new extension will be 4.5 minus 1.5. That's going to be 3. Do you guys agree?
Yes.
And on the other side, the extension is going to increase because you're moving, you're stretching it even more. So that will be 4.5 plus 1.5. That's going to be 6. Get it?
Yes.
Okay. Give me 1 second, please. You can write this down. All right, now think about this. So one by one, we're going to see what is the basically change in energy in both springs. So let's talk about spring 1 first. All right. Now, so that would mean that let's have a look. The first spring, I'm going to write the energy is half k, and I'm going to write the same formula that I derived, x2 squared minus x1 squared. Now see this. The spring constant of this is 16. The original, the this spring was 4.5 first, and now it's 6. So I can write 6 whole squared minus 4.5 whole squared. Do you guys get it? Like that.
Yes.
Now, why am I doing this? I'm doing this because, oh, by the way, I made a mistake here. I'm sorry about that. I need to change it into SI units as well, which is my bad. So let's do that first. I realized it was in centimeters. So first of all, I need to see that 16 Newton per centimeter would be equivalent to 16 Newton, and 1 centimeter has 10 raised to minus 2 meters. So it is going to be 1600 Newton per meter. So this will be 1600, and we can change 6 centimeter by dividing 100. So 6.06 square minus 0.45 whole square. Do you guys get it? 0.045.
Yes.
Like that. Sorry about that. Um, can you guys please help me find the answer to this?
0.0126.
0,
Oh, never mind. Wait.
So I got 1.26.
1.26 joules, right? This is what you got?
Yes,
Yeah.
sir.
Okay. The other spring will have a different energy stored in it. So let's do that now. So that one, energy equals to half times 1600 times, now initially it was 4.5, now it is 3. So we're gonna just do that. So uh, 0.03 whole square minus 0.045 whole square. All right, can you find this one now, please?
So it's 0.9.
It should be in minus,
Negative
because
zero.
Yes, sir, it's negative
0.9
0.9.
joules. Okay, now because why it is negative, because the energy in here would decrease because the extension has decreased. So now what we're gonna do is the total energy would be basically energy in spring 1 plus energy in spring 2. So it's going to be 1.26 minus 0.9. I think that's going to be 0.36 joules. Can you confirm, please?
Yes, sir. So X2 will always be the final extension.
Yeah, final minus initial.
Okay.
That's true. Okay, so now I just want to tell you one more thing, that because we want to find speed when it is released, the elastic potential energy will change into kinetic energy. Elastic potential energy was 0.36, kinetic energy is half mv square, so 0.36 half. The mass was 850 grams, so we're going to divide that by 1000 to change into kilograms times v square. Can you find the speed when it is released? When it reaches maximum speed, actually.
0.847.
0.847. Are you sure about that?
I forgot to square root it.
Yeah.
0.920.
0.92 meters per second should be your answer. Please have a look at this question. Let me know if there's any confusion in this.
No, sir.
Okay. So everybody's clear. Shazib, what about you? Furqan, Fatima, Farina.
Yes, sir.
So I just wanted you guys to learn how to use change in energy, and it's very important because a lot of questions like these will be there for 4 marks. This is a 4 mark question, by the way, so you don't want to lose marks in this. Okay. All right, kids. So when you're done, you can basically leave. Inshallah, tomorrow you're gonna complete this chapter. Try it.
Sir,
Yes.
it should always the answer should always be three significant figures, right?
No, no, no. That's not the rule, Himal. The rule is whatever data you are given in the question, it should be equal to the minimum data, significant figures, or one more than that. The data has three, you can write in three or four. Data has two, minimum significant figures two, so two and three, like that. Is it clear?
Okay, sir.
Yes. I will
Thank
see
you,
you.
sir.
Have a nice day. Bye.
Bye.